Okay, I think the number of people joining the meeting is trickling down now, so I think it's probably time to start. So welcome everybody to tonight's IGS Global Seminar. And this week I'm standing in for Tavy Murray. My name's Adrian Luckman. Tavy is on holiday this week. She had hoped to be here from her tent in Scotland, but for reasons that she may let you know next week, she is unable to make it tonight. So we won't be seeing her. But I'm very pleased to welcome to tonight's speaker. It's Doug Benn from St Andrews University. And I'm sure many of you already know Doug. There he is waving at you from your screen. Doug's very well known for, first of all, his textbook, Glaciers and Glaciation, that I'm sure he's too polite to give a plug to tonight, but I've done that for him. Of course, also his work on Himalayan glaciers, on carving processes, and of course on glacier surges, and that's what we're going to hear about tonight. So over to you, Doug.
Very good. Thanks very much, Adrian. Hi, everybody. So yeah, I'm really happy to have the invitation to give this talk to the IGS, because the IGS means a great deal to me, and I'm really happy to be able to talk to you about the work I've been doing on glacier surges. There we go. Hang on, I'm still getting the hang of this. Here we go. Right, okay, so I just want to talk a little bit at the beginning about my inspiration for beginning to think about glacier surges, and pretty much it came about through moving to Svalbard in 2006. And although only about 1% of the world's glaciers have recorded surges, a much larger proportion of the glaciers in Svalbard exhibit surging behavior. And while I was there, there was several spectacular surges kicked off, transforming the glaciers from very slow-moving, smooth, gentle beasts into these wild, crevassed, fast-moving, advancing glaciers. And as I began to think about surges, it became very clear that there's very diverse characteristics, and lots of different theories have been proposed to explain the surging phenomena. And different theories have been proposed to account for temperate glacier surges, polythermal glacier surges, glaciers on hard beds, soft beds, and so on. Now, around about that time, there was a paper on the surges of Trapridge Glacier by Frappe and Clark, and near the end of that paper was the quote that I've got up on this slide, which was, while it's clear, I'm not going to do a Gary Clark accent, but you've got to think of this as Gary Clark saying this. While it's clear that the thermal regime of the glacier will have an impact on its surge behavior, we think that this effect is collateral to surging phenomena rather than essential. To reflect the underlying dynamical unity suggested by the clustering of surge-type glaciers, models for surge mechanisms should be able to explain the entire spectrum of surge speed and structure observed within a geographical cluster, irrespective of the thermal regime of the glaciers. This really caught my eye because Gary is a very, very, very clever. And if Gary thinks that something's going on, that there's some kind of dynamical unity within phenomena that hadn't been previously linked, then it's a pretty fair bet that there's something going on there. And so I thought, maybe there is a possibility of a unified theory of glacier surges. And I decided to try and come up with something, to try and figure out what that thing might be. And over the course of the next while, I'm going to, there we go. Over the next hour, I'm going to talk about different stages of the work that I've done on surges over the last few years, beginning with a global analysis of surge distribution, then to talk about the enthalpy balance theory of glacier surges, and finally to present some observations that provide a test of some of the ideas proposed in that theory. Now the change is not behaving itself. Ah, there we go. So global analysis of surging glaciers. This is largely work that was led by my PhD student at the time, Heidi Silvestre, and we published a paper together on that in Journal of Glaciology for 2015, in which we conducted the first global analysis, the first analysis of surging glaciers as a global phenomenon, rather than the detailed studies that had been done on individual clusters up until that point. And what Heidi's work did was that it confirmed a hunch that I had, which was that surging glaciers occupy distinct climatic envelopes. I knew that there were big surging clusters in high mountain Asia, that there was a ring of surge clusters around the subarctic, plus one or two other locations in the world. And what Heidi's work demonstrated was that all of that collapses down to a distinct climatic environment for surge-type glaciers. Now, she used era reanalysis data to look at the preferences of surge-type glaciers in terms of precipitation variables, temperature variables, and so on. And the graph here shows a plot of mean annual precipitation versus mean annual temperature. Now, this is for era 40 cells. So this isn't at the glacier ELAs. They weren't able to correct the ELA data for the altitude of the glaciers because of the lack of knowledge about precipitation and temperature lapse rates. So this is just raw era data. It's a very crude but global data set that we're using here. So the gray bubbles are non-surging glaciers. The purple bubbles are surge-type glaciers, with the size of the bubbles according to the number of glaciers per era cell. And what we find is that the majority of surge-type glaciers occupy quite a narrow climatic range. Those of Arctic Canada occupy colder and drier climates than the rest of the surge-type glaciers, but only a few of the largest glaciers surge in Arctic Canada, whereas much higher proportions, much denser concentration of surge-type glaciers occur within the main climatic envelope. And Heidi also found that in all regions, and this is confirming work that had been done on individual clusters, that in all regions, surging glaciers have greater mean area, greater mean length, and lower mean slope than non-surging glaciers. We weren't able at this global scale to investigate geological controls, although on the scale of individual clusters, it's been shown that surge-type glaciers have a preference for sitting on weaker substrates, soft sedimentary rocks, and that kind of thing. Okay, so looking at this global data set, it reaffirmed on a global scale what Gary Clark was saying, that although there's great diversity within surge-type glaciers, there are repeating patterns, there are consistent patterns globally underlying the distribution of surge-type glaciers. And so this then gave me confidence to articulate the idea that had been brewing in my mind about why this should be. What is the wide scale, the widescreen explanation, if you like, or or idea that might unify, that might underlie all of surging behavior. And that idea is enthalpy balance. So we'll come to exactly what that means in just a moment. But just to begin with a couple of statements here about glacier dynamics. And that is that the mass balance of the glacier and its geometry determines the balance flux. In other words, that gives the glacier a goal, a target velocity, if you like, which will discharge the mass through the system. So we've got this balance flux, the flux that a glacier has to have if it is going to remain in balance. But at the same time, the flow rate of a glacier, the rate that the glacier actually flows at, is determined by its geometry and its enthalpy, particularly the enthalpy at the bed. And what I mean by enthalpy is the thermal energy of the glacier plus its water content. And in terms of basic characteristics, that is basically the ice temperature. Is the ice cold or is it temperate? And if it's temperate, how much water is there at the bed, at the ice bed interface within any deformable sediment close to the glacier bed. And so depending on the amount of water there is, the ice temperature, the amount of water, the glacier will flow at a particular rate. And for a glacier to remain in a stable, steady state, these two statements have to be simultaneously true. We need a glacier that's flowing at something close to its balance flux, and its enthalpy at the bed has to be such that its actual flow rate will match that balance flux. Now, these two statements are kind of coupled together, or the mass balance and the enthalpy balance are intimately linked. And one of the most overt links there is the fact that ice flow converts potential energy into enthalpy. So that, in other words, as the glacier flows downhill, it's giving up gravitational potential energy, and that is being turned into enthalpy in the form of potentially warming up the basal ice, melting water at the bed. And so this basically gives us a kind of framework for thinking about this, that for a stable, steady state glacier, the flow rate must match the balance flux, and enthalpy gains, any process that increases the enthalpy at the bed, must be balanced by enthalpy losses. So that gains like strain heating, geothermal flux, must be balanced by processes such as conductive losses and basal runoff. And the mismatched mass and enthalpy fluxes will lead to unsteady behavior. So that's basically the state that we got to in 2015, 2016. And the next stage was to turn that into a numerical model. And so at EGU one year, I cornered Andrew Fowler in a bar and got talking to him. And one thing led to another. I worked very closely with Ian Hewitt, who developed the full numerical form of this model. And so basically what Ian did was that he expressed my arm-wavy statements about mass fluxes and so on into a pair of differential equations, an equation for mass conservation and an equation for enthalpy conservation. And the mass conservation equation, both of these are expressed in simple 1D form. It's a kind of lumped model of the kind pioneered by Andrew back in the 80s, in which we don't consider spatial gradients on the glacier. We just think of the glacier as a column of ice that can thicken and thin and has nominal flow rates out of the system. Now, the mass conservation equation expresses differences in ice thickness in terms of the surface mass balance and the ice discharge out of the system. The enthalpy balance is strain heating, geothermal heat flux, conduction out through the ice, water discharge away from the bed, and rate of water input from the glacier surface. And we express the enthalpy variable in a way such that positive values indicate water content within the glacier, negative values are for cold ice, and increasingly negative values is increasing cold content within the glacier. So if you solve this pair of differential equations, what we find is that very interesting behavior emerges from this very, very simple model. So basically, if we specify the surface mass balance, the glacier length, the glacier slope, with just those as input values, air temperature is another one. So we've got these geometric and environmental, or geometric and climatic inputs into the model. It exhibits a range of different kind of behavior. Now, to introduce you to how we present the results of the model, I'm introducing you here to phase portraits. And what I've done here is I've has plotted up separate phase portraits for the enthalpy variable and the thickness, the ice thickness variable. So these plots show enthalpy on the vertical axis, normalized, ice thickness normalized on the horizontal axis, and the two panels show the rate of change of ice thickness on the left and enthalpy on the right. And this is for an arbitrary choice of climatic variables in glacier geometry. And what we see here is that on the thickness diagram on the left, there's a part of the diagram in which the trend of ice thickness, if you put a glacier down at that point there with a particular combination of basal enthalpy and ice thickness, it will follow that trend, that dH over dt will cause the ice to thin until it reaches that point. Conversely, if you arbitrarily start your glacier at this point, this combination of enthalpy and thickness, the glacier will thicken until it reaches that point. And this blue line is the H null line. It's the line along which dH over dt equals 0. And what we see is that for the ice thickness variable, no matter where the glacier begins on this, it will converge on a steady state. If we look at the enthalpy variable, there's part of the diagram where if you drop the glacier down into an initial state, drainage of water from beneath the glacier will reduce its enthalpy until it lands on that point, on that line there, the E null line. On this side of the diagram, geothermal heating and frictional heating will increase the enthalpy on the glacier. And in some parts of the diagram, that will cause it to converge on the null line. But crucially, in this bent over part of the diagram, the enthalpy diverges away from the null line. And that means that the glacier in this area here is in an unstable state, a state in which it will depart from its initial state. So now we can bring together these two elements of the phase portrait into a single diagram. Now, this here again is a enthalpy ice thickness phase portrait. Here's the H null-cline, here's the E null-cline, and in this case, the glacier, the crossover point of the two null-clines is on this lower branch of the diagram. And that is a stable point. That glacier can quite happily flow along at its balanced velocity, its enthalpy, production and losses is all in nice equilibrium. If we have a crossover in the upper branch, we've got a faster flowing glacier, it's a temperate glacier, it too is stable. But if our crossover point is here in the middle branch, then that is an unstable state. And we find that unstable solutions occur for particular combinations of climate, geometry, and basal hydraulic conductivity. So in other words, using a simple pair of differential equations to describe the glacier system, we find that that glacier can exhibit stable or unstable steady states depending on the climatic and environmental inputs to the model. So it's worth investigating what goes on in this middle branch. Why is this happening in the model? And the basic reason for that is that in this middle branch, the glacier is susceptible to a sliding heating feedback. Now we know that the frictional heating, which is the product of the stress and the sliding velocity, increases enthalpy. And as enthalpy increases, as the amount of water at the bed increases, according to our model, the drainage flux, the rate at which water flows out of the glacier, and the sliding velocity both increase with enthalpy. And the question is, which one is going to increase the most? These are the equations that we use. This is the water discharge with the hydraulic gradient, that's a conductivity variable, and this term here is a function of how much water there is at the bed. This is the sliding velocity, and this is pretty standard friction law expressed in terms of the enthalpy variable, standing in the place where effective pressure would normally sit in a friction law. And basically the behavior of these two functions, the discharge function and the ice velocity function, determines what happens. If water discharge increases more rapidly, then the enthalpy can drop down again and the system can stabilize. If the ice velocity increases more rapidly, you can have the feedback. So in other words, any increase in enthalpy increases the speed, which then creates more water, which can further increase the speed, and so on. So in our model, it's the relative values of these exponents, alpha and 1 over p, the relative values of those exponents in the sliding laws that determines this overturned branch in the middle of the enthalpy null-cline. Now that clearly is based on very, very simple functions, very, very simple characterizations of both basal drainage and of the relationship between effective pressure and velocity. These are complex things. And we've got them in very, very simple, simplified forms here. But I think that this does point to an essential truth, which is that the stability of the glacier depends on whether or not a sliding friction feedback can kick into place, and that is a relative response of drainage versus dynamics to an increase in enthalpy or water storage at the bed. Now, what we found further was that to attain this stable upper branch of the phase portrait, in other words, in order to get glaciers which are fast flowing, lots of water at the bed, and stable, not susceptible to oscillations, then we needed a two-component drainage system. And basically we kind of repeat the function that we saw in the previous one. This is water depth instead of enthalpy, but it's essentially the same. And in this term, alpha is less than Q over P, so that sliding winds when W is small, when the water storage is small, so the feedback can kick in. Here in this term here, alpha 2 is such that alpha 2 is greater than Q over P, and so for high water storage, drainage winds and efficient drainage can terminate the surge. And a steady state water flux is large enough to sustain an efficient regime, in other words, where this dominates, the glacier can be fast flowing without surging. Okay, so having kind of filled in how these phase portraits express the solutions to the equations, let's move swiftly on to consider polythermal glacier surges. And this is time series of the surge cycle of ice thickness, enthalpy, velocity, plus various enthalpy terms. And basically this is our surge cycle here. Long quiescent period, ice is initially cold, negative values of E, slow enthalpy gain from geothermal heating. As the transition occurs into a warm bed, the sliding friction, sliding heating feedback kicks in, and woof, the glacier goes into its surge phase. That's here and here. And then when drainage occurs, the surge terminates, and the glacier rapidly thins, and the surge terminates, and the cycle begins once again. And if we then look at temperate glacier surge, we find that the sequence of events is essentially the same, but without the glacier dipping down into the cold state during the quiescent period. So in early quiescence, geothermal heating is dominant, but the quiescent period is quite short because you don't have to slowly warm up the bed. The sliding heating feedback kicks in after not many years and initiates the surge. And so the argument here is that essentially temperate and polythermal glacier surges occur by pretty much the same mechanism if we begin to think about temperature and water content as being essentially manifestations of the same phenomenon. Our model also includes surface to bed drainage. We allow surface meltwater to reach the bed via crevasses, providing an extra potential enthalpy source. And we express the amount of surface to bed drainage by this function here, that surface melting, and beta, which is the proportion of the surface water that can reach the bed, and we scale beta to the velocity. There's a very simple way of saying that when the glacier is very slow moving, we assume it's not crevassed and no surface water gets to the bed. When the glacier is faster moving, it becomes crevassed and surface water can reach the bed, and we allow that to saturate at some critical velocity. And interestingly, when you do this, when you allow surface water to reach the bed of the glacier, as it speeds up during a surge, that affects the characteristics of the surge cycle. That it accelerates, it brings forward the surge onset, it causes the surge to happen sooner, because instead of having to wait for the friction sliding feedback to build up, once the glacier begins to surge, water can get down there and get it going. And we find that with surface water, surges have higher velocities and a shorter surge period. But we also find that surface water can also stabilize the flow. And that for some glaciers, in the middle of hundreds of other surging glaciers or dozens of other surging glaciers, if the balance flux is large enough, they can flow along happily at high speed all the time, like Kronebrain here, helped by the surface water reaching the bed through crevasses. The crevasses help to stabilize the flow. So basically now to return to the climatic pattern, the climatic preferences of surge-type glaciers, we can identify three different populations within this field here. For glaciers that are stable on the lower branch of the enthalpy nullcline, here these are small, cold glaciers, low snowfall, low balance flux. They're cold-based, that low enthalpy, and there's efficient conductive heat losses to the cold atmosphere up through the ice. So for thin, cold glaciers, they can quite happily flow steadily at low speeds. Bigger glaciers in Arctic Canada, we believe, are too thick to efficiently conduct heat away from the bed, and therefore they're susceptible to surging. If we go to the other end of the spectrum, we have high activity non-surging glaciers. Glaciers with high snowfall and mass flux, high velocity, high amounts of basal melting. Think New Zealand, high enthalpy, efficient drainage. So they're high enthalpy producers, but meltwater can evacuate that enthalpy very, very efficiently. And in between, we have surging glaciers, which have intermediate snowfall and mass flux, low conductive heat loss, they're in warmer climates, post meltwater production and drainage, and mass enthalpy cycling. And so we can define the temperature limits to the surge climatic envelope. All the small glaciers in the cold region, almost all the glaciers in the warm region are steady state. The precipitation limits as well, precipitation determining what the steady state mass flux has to be. What is the target that the glacier has to attain? So high accumulation, high enthalpy, turnover, low turnover, and in between the surging glacier. Now I must emphasize the title of this talk, that this is a widescreen view of glacier surging. Within within these broad generalizations, I'm aware that there's a great deal of nuance and detail. The geometry of a glacier, the details of its flow patterns, the details of the variation in climate and environment across the glacier. All these things are going to influence the way that surging plays out. But I believe that we have identified the underlying dynamic behind the surging phenomenon, the essential processes that must be satisfied if a glacier is to maintain a stable, steady state as against losing it and surging. And it's worth emphasizing that well over 90%, maybe 99% of the world's glaciers managed to solve their mass and enthalpy budget. They managed to do this. And so glaciers are obviously very, very good at solving their enthalpy balance problem. But in certain environments where the surge clusters are, Svalbard, Alaska, Yukon, Iceland, in these environments, glaciers have a really hard time balancing their mass and enthalpy budgets, and therefore they oscillate. So I'm going to finish up by presenting some information from a glacier in Svalbard. This is Morsnedbræen, which surged between 2013 and 2018. And working with Adrian Luckman, we collected a huge amount, a very, very rich data set on this surge. Velocity records, a succession of dams, glacier bed from the work of Johannes Furth, distribution of crevasses, and able to calculate key enthalpy budget components. And this is an animation that Adrian recently produced showing the surge of Morsnedbræen. Now in 2013, but back in 2013, we were able to ride snowmobiles up this glacier, right up into here and so on. And by the time the surge really kicked in 2016, the glacier was flowing very, very fast, very, very crevassed, and it blocked off one of the favorite snowmobile routes to the east coast of Svalbard. Am I going to be able to move on from here? This is the question. Here we go. And so I'll summarize the data now for you from that surge. From a succession of dams from 1990, 2010, 2014, 2017, we were able to define elevation changes on the glacier. And this is elevation versus elevation change, showing the pattern of elevation change on the glacier for different epochs. And basically during the quiescent period, this glacier has been quiescent since 1890, but from 1936 to 1990, the mass changes, elevation changes on the glacier, pretty much followed the mass balance curve, with thickening on the upper glacier, thinning on the lower glacier. Between 1990 and 2010, we start to get a bulge forming in the middle glacier and drawdown on the upper glacier, a pattern that strengthened between 2010 and 2014, increased drawdown, migration of the bulge down glacier, and then once the surge is really kicking off, massive drawdown on the upper glacier, massive thickening on the lower glacier. Velocity archive, first of all using TerraSAR-X data from 2013, 2014, 2013. Adrian was able to show where the surge began, how it evolved. And then in the later part of the archive from 2016, using Sentinel data to provide this sequence of velocity data. This is distance along the center line here, this is time there. And from the sliding speeds and from the observed velocities, calculating creep velocity, deriving sliding speeds, in conjunction with calculated stresses from the evolving glacier geometry, we're able to calculate the changing enthalpy production from frictional heating beneath the glacier. And what we find is in the earliest period, 1990 to 2010, we have enthalpy from frictional heating in the upper part of the glacier. This is here the value for geothermal heating, that dashed line there. So in the very late quiescence, we've got detectable frictional heating, but it's still less than the geothermal heat flux. Between 2010 and 2014, frictional heating overtakes the geothermal flux and migrates down glacier. And then as the surge really gets going, the frictional heating increases rapidly, an order of magnitude higher by 2014 than it had been 4 years earlier. This is a trace of surge peak and termination. 2016, there's the surge peak, and the termination is slow and gradual. So an initial rapid decrease in velocity, and then slow decrease in velocity with summer speed ups. There. And what we see is that the termination of the surge coincided with the surge front reaching the glacier terminus. So the surge front was traveling down through the glacier, and when it reached the glacier terminus, the speed began to decline. So that's an interesting thing. Why is that? Well, we found that when the glacier reached the terminus, when the surge front reached the terminus, there was a massive discharge of water into the fjord. And you can't normally visualize meltwater plumes with Sentinel data, which is from backscatter, but this is ice, plumes of ice emanating from the front of the glacier and swirling around in the fjord. And we interpret this as frazzle ice from super cold water. Pressurized water escaping from underneath the glacier, depressurizing and forming frazzle, and that is carried away from the front of the glacier. And if we look at the timing of these releases, we find it has a discharge event in August, September 2016, but the biggest one coincides with the glacier reaching the front, reaching the terminus, the surge front reaching the terminus, and we think a good connection could then be made between all this stored water beneath the glacier and the glacier front. So actually we find that the sequence of observed changes on Morsner Brain, the idea that geothermal heating was pretty much the only enthalpy source throughout the whole of quiescence, until gradually frictional heating kicks in. Sorry, excuse me. Frictional heating then encourages glacier speed up, causing more frictional heating. The speed up opens crevasses, causing a rapid acceleration of the ice due to a second feedback, a crevasse velocity feedback. And finally, when water discharge exceeds inputs, termination occurs. And so the sequence of reconstructed changes on Morsner Brain actually matches rather well the modeled sequence of changes, even though we're dealing with a very, very simple model. We think it does capture the essential processes. And to briefly turn to temperate glacier, the classic surge of variegated glacier, which was quiescent between 1966 and 1981, and then surged 82 to 83. The data set that was collected by Barclay Cam and his team was so good that you can actually go back to that and interrogate it and reconstruct the frictional heating that occurred. And actually what we find is that there is an exponential increase in frictional heating beneath variegated glacier during the second half of quiescence. So regardless of what other mechanisms were going on underneath that glacier, it is undoubtedly true that the gradual speed up of the glacier in late quiescence did cause an increased production of basal meltwater, which in turn would have encouraged higher velocities. So there was sliding friction feedback going on in the second half of quiescence in variegated glacier. And I would argue that rather than the standard model of there being some kind of a flip from a channelized to a distributed drainage system sometime in 1982, causing a sudden transition to the surge, I would argue that actually the origins of the surge can be found in the second half of the quiescent period, when friction sliding feedbacks were gradually gaining pace, and that what actually really kicked off in 1982-83 was extensive crevassing on the glacier surface, which allowed massive influxes of surface meltwater at the onset of the melting season. And that's what caused the spectacular phase of the surge in 2 successive years. Okay, so to kind of draw this together into a few conclusions, arguing that temperate and polythermal glacier surges can be explained by the same physical system, the same physical principles. And this is that velocity heating feedbacks occur because enthalpy losses cannot balance enthalpy gains for the particular configurations of these glaciers. And that spatial variations, things like topography, mass and enthalpy gradient, whether this part or that part of the glacier bed is warm or cold, that creates the rich variety that we see. And so I propose that enthalpy balance theory can explain not only the underlying unity in surging glaciers, but also their diversity. And so where next? Well, there's lots more that we can do with this line of inquiry. I'm very interested in looking at transient forcing. So far, we've just looked at steady state climates and what kind of glacier behavior emerges under these. What happens if you transition from one climate to the next? What happens if you do that over a cycle that's longer or shorter than observed surge cycles? So you have a variety of behavior that could emerge from that. At the moment, we're just doing a simple 1D model. Obviously, good to go spatial, although then you're confined to interrogating individual cases rather than exploring a parameter space in the way that we've been able to do before. Surges triggered in the ablation zone. We've been doing model experiments with a model glacier ablation zone where you have inputs to the system of ice from up glacier and meltwater from up glacier, and lo and behold, we find that for some combinations, surges can be triggered for very much the same reasons. And of course, as I say, this is a very broad brush view of surges, and we still need to do much more detailed examination of hydrology and basal processes to look at exactly how the kind of processes I've been talking about play out in detail and in the individual cases. Thank you very much.
Doug, absolutely brilliant. Thank you so much for that. Really fascinating. Now, you've got an audience here of 85 people who've been every word there. And I can see some people have switched their cameras on and applauding you quietly in the background there. Look at them all.
Yeah.
All that quiet applause. Okay,
Yes, excellent.
people here, and I imagine there's going to be quite a lot of questions. So can I invite you, if you do have a question, to put that in the group chat, and as they come up, I will try and pick them out as I see them. And
Right. Now, in terms of viewing the chat, I might have to stop sharing, which means that I can't necessarily jump back into looking at slides in the presentation. So
I think you should be able to see the group chat even though you're sharing, but I might be wrong. To jump out of the presentation if you have to.
Yeah, I'm just trying to find where that group chat might be.
I mean, don't worry, Doug. I can read out the questions, or I can invite.
Okay.
So let's see if any questions appearing there now. So if you've got a question for Doug, please stick it in the chat, and I will invite you to switch on your microphone and ask him yourself. The comments so far coming in are applause and thanks, Professor Doug, for your great work. Greetings from Chile. And here we have a question from Richard Katz. Richard, would you like to ask that question yourself?
Hi, Doug. If sliding modifies the transmissivity of water in the basal system, how might that affect the feedback? I mean, we understand the basal system in terms of the cavities that open up due to sliding. So it seems like these things could be linked, and I didn't see whether that was actually, that link was made in the model.
Yeah, no, it's not. That in the model we use a very, very simple description of the drainage system in which the water flux is simply a function of the hydraulic gradient, or indeed the topographic gradient beneath the glacier. We don't have variable ice thickness in there, so it's a function of the topographic gradient and the thickness of water storage within the system. We simply builds up as a linear function of water production. So we don't have any fine detail like that, but of course you're exactly right. As the glacier speeds up and cavities open, you're potentially opening rootways, and that would be an additional possible feedback that could, well, negative feedback that would encourage more efficient drainage and stabilization of the system.
Okay, thank you, Doug. Thank you for that question. We've got a couple of questions from Rob Larter and one from Will Koshitsky. So Rob, would you like to come on and ask your question?
Right, I have a microphone here. Yeah, so when you were looking at the correlations, Doug, one thing that stuck out for me was the surging glaciers tend to have lower slope than normal.
Yeah.
So, and it seems from other things you said that the efficiency of the basal hydrologic system is critical, because you're saying that's the explanation for some of the high precipitation areas.
Yeah.
Not surging. So,
yes.
I mean, presumably if you've got lower slope, you generally got a lower hydrologic gradient. So is that a way of looking at it?
Yes, absolutely. That I think is probably the main reason why slope is such an important predictor. I think it's almost certainly the hydraulic gradient. And this is kind of interesting because Gary Clark puzzled over these correlations many years ago, and one thing that he was unsure about was whether glacier length and glacier slope were genuinely independent variables, or whether it was simply because there was autocorrelation between those things. And I've spoken with Gary about this, and we think that length and slope are two quite distinct controls on surging, and that hydraulic gradient is the slope, actually, another reason for the length is also a drainage efficiency thing. You know that if you've got a longer hydraulic pathway, there's more chance that the system's going to get into trouble somewhere along it.
Okay, Rob, while you're on, can you ask your second question, and then we'll go over to Will Kachitsky.
Yeah, well, I noticed there was a preponderance of surging glaciers in Iceland.
Yes.
And I wonder if that's connected to the fact that throughout Iceland, you're going to have pretty high geothermal heat flow because of its geologic situation. And does that kind of set a naturally high bar for positive enthalpy, so which predisposes them to being surging type?
Yeah, the interesting thing about that is that that high enthalpy production is not high enough to kind of take them into the temperate, you know, the high activity non-surging glacier envelope. So I think I think the high geothermal heat flux in Iceland probably makes the surge cycle shorter than it would otherwise be. But I don't think it's a primary cause of that particular cluster.
Okay.
Okay, well, thanks for those questions. Is Will there? Can Will switch his mic?
Yes. Hi, Doug. Thanks for a great talk. I was wondering if you could comment on the surge repeat interval, and if you could predict that for various glaciers, perhaps by climate or the geometry, or maybe something else that's causing these to repeat at different intervals. I'm thinking in particular, we have temperate glaciers in Alaska, Yukon that are repeating at on different time scales, 5 versus 30 years, say, yet they're right next door to each other.
Yeah. The question of the surge period is one that we have yet to resolve, and this is one that Hester will be very familiar with, because she was my editor when we were submitting these papers, and it was one of the points that she grilled me on. And the thing about the surge interval is that we know the range of things that control it, and it's traditionally thought of in terms of the snowfall and the amount of snow needed to build the glacier up to a certain level. But if you flip that round, the build-up period also depends on how much the glacier has been drawn down in the previous surge. In other words, how much has it got to go back up? And that amount of drawdown depends on the velocity and the duration of the surge phase, which in turn are caused by a whole range of factors that control velocity, that control the rate at which water builds up at the bed, the rate at which it can escape, and so on. So there's actually quite a range of interacting factors that influence the length of the surge period. And with the model that we, as we have it at the moment, key processes such as the drainage and the relationship between water content and velocity are so simplified and so highly parameterized that even though we could have tuned the model to match observed surge cycle lengths, we weren't satisfied that we would have the right solution to that. There's too many degrees of freedom. And so we opted in the initial publication of the model not to tune it to match particular surge periods. But I think this is something that we're going to have to grab by the horns. It's something we're going to have to engage with. So yeah, it's an important thing. And if we can start to be in a position where we can predict and explain variations in periodicity in different systems, then we'll really be getting somewhere.
Right. Well, thank you very much for that. I can see on chat that Ian Hewitt's weighed in and Richard's given some answers. I can't see any more questions appearing there. I think it's just some chat that's sort of weighing in on your previous answers, Doug. No more questions are arising. I can see people are starting to leave. So I think perhaps this is the time to draw it all to a close. Doug, can I invite you to move to your final slide, please?
Yep.
So this is a reminder that there will be another seminar next week, September the 16th, same time, normal place. And this is Ginny Catania from the University of Texas, and you can see the title there yourselves. So that's next week's. So we just finish off now, and in the normal style, if you would like to do so, please switch on your microphones now and thank Doug with a jolly hearty round of applause. Thank you very much.